Hi folks, welcome to another episode of NYC CNC. Today we're going to continue on with the Arduino CNC project, and we're going to work on this homemade DIY Arduino CNC driven by the GRBL shield. An awesome project, and the focus on this one is really inexpensive parts. The linear bearings, the ground linear rails, incredibly inexpensive timing belts. We're going to walk through all that, how to interface it with the GRBL, get some code up and running, and then hopefully at the end of this we'll be able to export G-code and use, I think we'll try to fit a pen inside of that thing and do a drawing. Let's dive right in. If you haven't seen the first video yet, here's a screenshot and there's a link. You click right on the video screen to pull up the first video. That's where we walk through the setup of the GRBL shield and the Arduino and some of the very basic settings. Today what we're going to do though is mix that in with the hardware, actual measurements, and get this thing really running. Let's take a quick look at the Solidworks Cad Model. And I want to thank Craig Kelly. He's a longtime viewer who was really instrumental in getting this CAD model put together and did a lot of work on it. So Craig, a big thanks for your help on this. And what I love about Craig's work is that he's not only is he great to work with, but he understands simplicity, and that was the goal here. Let's make this thing as simple and cheap, not for the sake of being cheap, but for the sake of figuring out what can we do with a low-cost machine, and one that's hopefully easy for you folks to make, because that's what I really want. I want everyone watching this video to be able to do this. If you need one that's more rigid, you can do that, and we're going to do that actually pretty soon on a project involving proper linear rails, but you're talking about hundreds of dollars just for some of the linear motion parts alone. So, as you can see here, the idea for me is to be able to dispense parts into a hopper as this tube moves around. We don't need to worry about the trays below right now. You can see we've just got 4 pieces of angle bracket. Craig had machined them down, but if you take a look, or in the SolidWorks had modeled them down, but if you take a look on the actual thing I left them all as 3-inch aluminum angle, 1/4 inch thick, and that'll be fine. You've got to get some holes drilled to hold your bearings. I actually have just, I thought I was going to oversize drill them a hair and then ream them, but right now they're just press fit in there. So again, we're just trying to get it done quickly, folks. And then as you can see in the CAD model, there's not a split line shown, but the idea is that a screw would hold the timing belt together, because the best way to purchase timing belt material is the large spool and then you cut it. So obviously you either need to splice it into one solid belt again, or what's much easier is to leave it as an open-ended belt. I did the same, and you can see right here there's a steel bracket, and inside of that bracket are the 2 ends of the belts. I did the same thing on the x-axis. I'll flip the camera around here so you can see. The belt is secured by the the screw right there, and then this screw is threaded through the aluminum angle, and it acts as a makeshift tensioner just to keep the right amount of tension on the belt. So like I said, I put it all together, and I'm really happy with the results. You can see you've got great motion on both directions. You're going to find that the X is way longer than it should be. I didn't want to cut the bars down yet. I will later, because this machine only needs to be cover an X distance of about 10 inches. But for now, I figured let's have some fun. And it's great. For those of you who don't know, the way these work is these are linear bearing blocks, and they actually have recirculating balls inside this black ring here, and they allow to a very low friction and accurate way for these to slide over these linear bearings. I'm pretty happy with the Y. The X, as you'll see, has some play in it like that, and that's totally unacceptable for any sort of 3D printing or cutting application. This will be fine. The way to improve that easily would be to make a longer Y-axis support piece, or the piece that travels along the X rather, and then to use 2 of these on each one. But I'm also not too worried about it, because let's talk about cost. Folks, I'm finding these bearing blocks for well under $5, the steppers for under $10, the rail is like $6 or $7, timing belt is super cheap. There are links to all this stuff in the video description right below. So if you want to purchase this or just explore more, please by all means click on those links to see sort of how I put this together. But folks, we're talking cheap. All the linear motion parts, including the steppers, are like under $70. The aluminum for me is really cheap, and then you've just got to add your GRBL shield, which is $50 in an Arduino, and I think that's about it. We are planning to offer the aluminum brackets for sale on the Saunders Machine Works website, just because we know there are some folks that don't have the ability to easily machine this stuff, and it's easy for us. So if you're interested in that, you can check out, by the way, we have a brand new website. But again, the point here was, how much fun can we have with a pretty darn inexpensive CNC setup, if you will? And then the other question is it accurate? Well, let's take a look. So accuracy, let's test it. For those of you who aren't machinists, we've got some basic machinist tools here that also, fun fact, are not expensive. I'm using some 246 blocks. These are a little bit less common. They were actually something that I featured in my 2014 10 machinist Christmas gift ideas video. And they were a big hit. I had a number of folks who were like, these are awesome, it's a great price. Anyways, on them is a very inexpensive magnetic indicator holder, and then this thing which is called a dial indicator, and it has a ram on it, or shaft, and as you push that shaft back, it measures distance, and each tick is 1/1000th of an inch. For those of you who aren't familiar with that, a standard sheet of printer paper is about 4,000. So it would take 4 ticks to measure the thickness of one piece of paper. So in other words, these things are pretty darn precise. You can see them move right here. So let's do this. I've got it set up here with the plunger against this, one of the linear bearings that's going to travel with our X motion, and I've got this thing preloaded. Now the first thing we're going to do is not measure accuracy, but rather repeatability. In other words, I don't care how far it goes, I care does it come back to the same point. So we've got it set up here. I'll just twist this so we're right on 0. Now let's type in a relatively arbitrary distance, G01 x negative 0.4. Hit enter. Okay, it moves to some distance. Now we'll go back and type G01 x 0, and the million-dollar question is, how close to 0 do we get? 0.002, that's pretty darn good. I will take that any day. Remember folks, we're using very inexpensive parts. They're not rigid. There's lots of types of looseness. Even wiggling the aluminum right there gives you play of quite a few thousandths. And again, I'm okay with all that. I still think this is just amazing. Now let's take it one step further. Got the needle lined up on 0. I'm going to click send. This program goes further, and it's pausing at the end of each stroke, just so you can sort of see. It'll go, I think, 7 times, so maybe that's 3. And you can see it seems to be repeating within about, well, that was right on 0, plus 1 thou, plus 1 thou, plus a thou, yeah, maybe not even a full thou, maybe half a thou. So you guys saw it back and forth about an inch 7 times, and you're holding tolerance. Again, I'm not trying to say that this is a revolutionary CNC machine here. I'm just trying to say, with this inexpensive components in a relatively flimsy construction, we could do some really cool stuff. So let's keep running with this. In the introduction of the video, I ran a intro G code. Let's take a quick look at that, show you just how easy it is. G01 just means we're moving at the standard rate versus G00, which is a rapid. So we're just saying go G01, go to Y2, x negative 8.5 at a feed rate of 300. We'll get into what that means later. Then go back to Y0, x0, and there's no reason for a space here other than my own preference to see a break. Then go just over to the x. So here, let's think through this. So this should be x and y moving at the same time, and that should be as well. Now we're just going to go over the x. Then once we get to the x position of negative 8.5, we'll go up 2 in the y, and then we'll go over in the x, and then we'll go back in the y. So this should draw a box versus this up here, which is a diagonal. Then we go to a fixed position here of x of 1, y of x negative 4, y 1. Then we increment over in 0.2 x's, as you can see here, 4.2, 4.4, 4.6. And in between each one, we have a pause, G4 of pause 0.5, or 0.5 seconds. So let's take a look at that now that you've seen the code. And so we'll just go to Browse, Sorter, Open, and we'll run that code. And you can see, again, we should have a diagonal first, then it should draw a box, and then from the home position, it'll come somewhere here in the middle and index over a few times. There's our box. And then here's the indexing over. Pretty cool, right, folks? So we know G-code works. Now we need to figure out how to make use of it. So now we do need to get into some math, and it's not in any way hard, but well, there's just no choice about it. So in the GUI, and by the way, folks, I really appreciate a lot of folks recommended there are different and even better user interfaces for GRBL out there. I need to check those out. So let's talk about the math. We need G-code that makes sense in terms of how far the distance is to move. So let's take a look at something. If we print $, enter, we get the parameters that GRBL came with. The most important ones are the first two. What that is the distance per step. You remember from the first video, we had this little scratch Excel file where we did some basic math, and we said that we knew it's 200 steps per revolution of the stepper, and so if there's, right now it's the GRBL set at 250 steps is 1 millimeter, so to make the steppers go 1 revolution, it would need to go G01 x negative 0.8, and that sure enough proved that the steppers went 1 full revolution, which is great. Well, now we've got a different factor. We've got the factor that we're not driving directly from the stepper is driving a timing pulley. The timing pulleys right here measure 3/8 of an inch on our dial calipers. So math is pretty straightforward. We just simply do pi times the diameter times the number of revolutions. So 375 times 1 revolution times pi means 1 revolution of our stepper motor should move this 1.178 inches. Great. Let's see if that's true. We've got the dial indicator back set up here. Got it on 0 preloaded. We'll go into GRBL and we'll just type G01 x negative 0.8, enter, and it goes past it. Goes to 1.25. So about 70 thousandths past it. Here's the thing, I'm actually not worried about that right now. Just to prove if we go back to 0, should be pretty accurate. G01 x0. Again, we're right, look at that, folks, right on 0. The reason it's going a little bit too far is that we're actually a little bit wider than 3/8 on our pulleys. Okay, so we thought 200 steps, which is we know is 1 revolution for sure, would go 1.178. That's what I've got right here. Ends up that it actually went, if we look back at the dial indicator, about 1.256. So we'll put that in here. So what that means in millimeters is 31.9. And so we want to know, okay, well, if 200 steps is 31.9, then that means 1 millimeter is 6.269 steps. So when we go back to the GRBL setup file and we see this first line, it's asking us how far should I turn a stepper to go 1 millimeter. So we need to change that from 250 down to 6.269. So we'll do that by just typing $0 equals, it's here, 6.269, enter. We get an OK. We'll check our parameters by opening them up again, and boom, there we go. Now, if you're wondering, wait a minute here, why did we go from 250 all the way down to 6? The answer is simple. We're doing effectively a direct drive output from the stepper to a timing pulley. Normally, you'd be using a lead screw, and a lead screw has a much finer pitch, so you have to turn the motor a lot further to get the same motion. For us, the same thing will hold true for the y-axis, so we will do $1 equals 6.269. Just quickly check that. Perfect. But now we've got a problem. If we say G01 x negative 5 millimeter and hit enter, look, it's got this nasty jerky motion to it. Here, we'll go a little further so you can see G01 x negative 15. So we got to update a couple more settings real quick. I went ahead and was playing around with this earlier, so let's just look through what I came up with here. Default. So we want to change we've already changed 0 and 1, obviously. We want to go ahead and change 3, 4, 5, and 8. 8 is one of the most important ones. So we'll do 8 as 500. That's up from 100. And I think that was the big difference. So $8 equals 500. Now we'll try G01 x 0. Oop, no, I lied. 4 and 5 are big. So 4 equals 2,000. $5 equals 2,000. Okay, and now we need to type in the feed rate for the first time to force it to update. And we want to go at 2,000, F2000. So G01 x negative 15 F2000. Boom, look at that. And then we'll go back to 0. I think you can now just type in x0. No more need for the feed because it carries the feed forward. And look at that, we're 2 thousandths shy. We'll repeat that again. Still less than 2 thousandths off. Awesome. Now we're getting somewhere. Okay, now our most important test yet. In theory then, if we go x negative 20, that's 20 millimeters, it should go 0.787, that's the inch equivalent, which I have to use because my dial indicator is in inches. So let's hop over here, G01 x negative 20, boom, and let's take a look. We are at 786. Holy smokes, folks, we're 1,000th off. Nothing wrong with that. That's sweet. Okay, let's see if this thing we built's worth anything. I have got in SolidWorks a CAD model of my company's logo, Saunders Machine Works. And for those of you that are watching this video, but it may be new to my channel, a lot of what I do is machining and CNC work. So, and in fact, we just started a series called Choose Your Own CNC Adventure, where we had over 100 folks send in metal and plastic type of parts that they want to understand how they would be machined or manufactured. So if you're interested in learning more about the process of machining, I would welcome you to either subscribe or to check out some of those videos. But what we're going to do is we're going to take this CAD model and we're going to export it via this little button right here to Sprutcam. Sprutcam is what creates the G code for the manufacturing process. So again, CAD is what you use to sort of build the house, if you say, or the architectural style. CAM is what you then do to say, okay, I need to cut here and drill here and nail here, if you will. So what we can do is we're going to do what's called a 2D contouring operation, which is going to just follow along 2D contours or curves or lines, as you might think. And for those of you who had followed my SolidWorks or my Sprutcam videos, you know I like to be sneaky in how we select these lines. And rather than mouse over each one and hold down Control, we can just turn off the surfaces, view it from the front, click and drag that. Now hold down Alt and drag like so, and now you've selected just the ones you wanted. Oops, somehow we missed one. Hold down Shift and you can finish those few up. And now you've got the geometry we need by just selecting curves. I already did this in the operation right here. Look at some of the parameters. Tool won't matter because we have no Z axis or even a spindle here. We want to run at 3,000 millimeters per minute. And again, this doesn't matter. Only thing I did was I smoothed out the arcs just so we didn't have too much jerkiness. So what this does is when you post-process it, that's a process that involves creating G-code that's bespoke for certain types of machines that need different parameters to start and stop and so forth. The generic code will work pretty much just fine. So I'll click Run, and we get this G-code right here. Now I need to delete this stuff in the beginning because GRBL, it's just comments. GRBL doesn't know what to do about that. And then I need to delete the, this is a tool height position that's, again, custom to my machine. Not a big deal. Just, I think there's one at the end I need to clean up. And now this is a basically Cartesian coordinate system that's called G-code that should let us use the GRBL to engrave or mark this logo. So in Universal G-code Sender, we will browse, we will open that file, and then here's what's cool. Click Visualize. Boom, look at that. That's pretty cool. Now, hopping back to the machine itself, what I did was I just cribbed up a piece of aluminum with a sheet of paper on top of it that gets me pretty close to the right height. We'll see. Cut me some slack, folks, if this isn't 100% perfect, because the point of this machine isn't to have a Z like this pen or an engraver. We're going to do one on that, though, here in a few weeks. So I'm hoping that this will come out okay. But the idea is to use this Sharpie to trace this logo on a piece of paper. Again, folks, we're talking about such an easy thing to build, so inexpensive. I think this is cool. I've talked about it in my channel before. We live in a great era. To have these tools at our disposal and be able to do this stuff, I think is awesome. So let's get this thing set up here. So I'm going to take the pen cap off. What we're going to see is it's going to be tracing some lines around as it finds, goes to a certain position. So the logo isn't going to look perfect because we don't have a Z retract. Again, we could build one, just not the point of this specific machine for me. So let's see if this will work here. Let's come in from this side. Looks like my pen's a little low. Pull up, there we go. Okay, so again, bear with me, folks, because we've got some smudging. I think I'm going to have to just sort of put a little bit of tension on this so it doesn't move. Now, let's see here. I've got the file ready. We're in the top left corner, which is where I want to start. So I'm going to click send, and then we can actually use the visualize box to watch along. So without further ado, send, visualize. Here we go. Holy cow. There we go, a little bit of light pen. It's okay. Here's the W. Oh, this is actually working much better than I thought. I thought the pen would be, I thought there would be more vibration or variance. There we're getting a little bit of a light line. This is great, folks, holy cow. S is a little jerky. I got to work on that. But that's it. Look at that, folks. In a few seconds, it's like our own little pen plotter. This has really been one of my favorite Wednesday widgets, folks. I was a kid. I went to a museum in Columbus called COSI, stands for Center of Science and Industry. And they had a machine there. It was almost like a KUKA type robotic arm, and you could, I can't remember whether you could ask it to draw your name or it would just draw a pre-programmed name. It was beautiful. I mean, harmonic drive, speed, precision, a lot more than this thing. But nevertheless, that made me as a kid know I want to build robots like that. I want to be able to do that. And in some respects, I never got there because that's not what I do. But look what we just did, folks. And you can do this too. It's so easy. It's so inexpensive, and it's awesome. So I'm going to keep running with this project as the hopper design. We're also going to be building one again with linear bearings that is going to be much more rigid for an actual cutting application, so stay tuned for that. I want to thank Tormach. They're the sponsor of these videos. They help put these content out. They help allow me to dedicate the time to these videos. They actually using the Tormach vices here to hold up this setup for just to make it rigid and easy for the videography. So thanks to Tormach. If you guys are interested in this stuff, please comment, subscribe, thumbs up, share it with your friends. It means a lot. I'm at 35,000 subscribers, which is incredible to me. I'd like to get to 100, which seems insurmountable right now, but I'm going to try to keep putting out good content on Arduinos and CNC and manufacturing and prototyping, and we'll take it from there. So with that, folks, take care, stay well. I'll see you soon.